Yeah, so the sun, earth, and moon, it's obviously a very important thing. We all need it. The sun's right here. It's a bit cloudy here in Canberra, so I can't fully see the sun outside. But I will use my fake earth later. It's a little inflatable earth, and I even have a little Lego astronaut there. This will play us here in Australia for our demo, because we're going to really focus on how the sun, earth, and moon work together. I really like starting with this video. So this is a video we actually took by essentially just attaching a GoPro to a balloon and sending it up. We're about 32, 35 kilometers in the air. That's why we're a bit bouncing around. You can just start to see the curvature here, but there's some effects with the fisheye lens. You can see how thin the atmosphere is. You can really see the difference between where the Earth ends and space begins. Now, here's a fun legal fact. Space starts at exactly 100 kilometers. That's the legal definition of space. And the reason we have that is we have to have this definition of where space begins, and you can actually say you're an astronaut. It doesn't actually matter, and we can't use things like where the atmosphere ends, because the Earth's atmosphere extends for thousands of kilometers. There's even a little bit of atmosphere where the space station orbits, just enough to slowly produce some drag and bring it down. There's things like we can't use gravity and all sorts of things. Now, I know we're already getting some good questions. Are aliens real? I haven't seen aliens. We'll get into it soon. But in a couple weeks, we're actually talking about looking for life and all what that means. I do think life exists here. And that's because there's lots of things like the sun and earth and moon that we think can create life. Now, we have to start with the sun. This is what essentially is the driving force of life here. Now, you might have heard that the sun is this big, hot ball of gas. And that's pretty much right. The sun is this huge amount of gas, mostly hydrogen, a little bit of helium, some other things in there. And it's churning it. It's actually smashing the atoms together, as we call it. It's kind of like a big nuclear bomb, but a safe one. And in turn, it's producing a bunch of energy, a bunch of heat that goes out into space. And as that heat goes out into space, that's where we get our sun and our heat and our daytime and our warm temperatures. And it's really what gives us life. And now the cool thing about it is just as a fire. So if you're around a campfire or even the stove at home, don't touch it. But the further away you get, the colder it gets. And that's the same thing in space. The planets that are further out, there's less heat that gets to them. So Earth ends up being this very special position where we're close enough to get enough heat to keep us warm and to give us life, but not too far or not too close, so we get cooked. You know, Mercury's pretty hot. Venus is really hot. We'll talk about that more next week. And so the Earth really is this special thing. Now, we just had a question about the first video I'll answer. What happens when the balloon pops? So we actually have this parachute that comes and lands everything down, and we have this cool chase and hunt it. So luckily, we're pretty good at recapturing it, and it actually brings down most of the balloon with it, so we don't pollute. Now, a bit about the sun. Now, the sun is quite big. You can fit 1,000 or so, just above 1,100 Jupiters inside the sun. And you can put about 1,000 Earths inside Jupiter. So you can put about 1 million Earths inside the sun. It is huge compared to what happens here on Earth and our size. Now, the sun is really in its middle age. It's about 4.6 billion, so 4,600,000 million years. It's quite old. And so it's been around, it will be around for about another 5 billion years until it turns into a red giant. And as it turns into a red giant, it will grow, and it'll slowly get closer to the other planets. And we'll talk a little bit more about that next week. Now, someone just asked a question that's actually quite good to this. What would happen if the sun was half its size? Interesting, because it actually means, let's say we shrink the sun right now. Well, the heat wouldn't travel as far as it does. It also would produce a lot less energy, which means it immediately become colder on Earth. It would also change the way our orbit works. So our spinning around the sun, and we'll talk about that in a little bit, because it's actually our sun that helps drive not only life, but how we partially move around it and in relation to the moon. Now, the sun is quite cool because sometimes the sun burps. Now, I like a good sun burp because when the sun burps, it produces these huge waves, what we call of energy, and this travels all the way through space. And so you kind of see a very complex diagram, but don't worry too much about it. But what you see here on the right is we have our Earth, and we have this big bubble around us, this giant magnetic bubble. So just as those magnets you stick on your fridge, our Earth has a big one. And this kind of protects us from a lot of these incoming waves of the sun. And as these waves of what we call the solar wind and coronal mass ejections, kind of these sun burps travel through space, they can sometimes make funny noises. So you can really hear a bit about how this sun is kind of reacting. And that's this very active sun blowing literally through space. So hopefully you're all hearing that perfectly. We always have some fun things. Oops, sorry. Now, I kind of like this video a bit more because it's a bit more chirpy. And these are what you're hearing now is actual measurements from the sun. So let me, I can't hear the audio. Let me just change this real quick. Sorry about that. Technical difficulties, it never works according to plan. Let's try this again. Hopefully you're hearing this. So you can kind of hear almost like birds chirping, hopefully. And so what this chirping is it's kind of like this bubbling coming from the sun, kind of like a stove, a water bubbling on the stove. Now, if we play another frequency, this almost sounds like Star Wars phasers. And this is really bursts of huge amounts of energy actually leaving the sun. This is real measurements. Now, you can't hear this directly in space. That's because it's not quite the sounds our ears can pick up. So what we've done is change that to make it something that we can hear. This is my favorite. It really sounds like waves on the beach or wind blowing through space. And so this really is as the light is traveling through space, slamming into Earth. Now, this produces something really cool here on Earth, one of my favorite things, the aurora. Now, if you've ever been lucky to see this, so sometimes in Tasmania and the southern parts of Australia, we can see the aurora australis. Or if you've ever been in the northern hemisphere, you can see the aurora borealis. You can see these waves of sunlight, essentially these burps traveling through it, hitting our Earth's atmosphere and lighting up the sky in these beautiful colors. So it's really kind of lighting up the air in our own atmosphere. And this is probably one of the coolest things I've ever seen. I hope you enjoy it. So some astronauts on the space station, as they were orbiting around, they had a camera outside and they were able to see the aurora from space. So what you're seeing is there's a camera underneath the space station and we're looking down towards Earth. And what these brilliant waves of green colors are is these sun bursts, these ejections from the sun, these bursts of light and energy that has traveled through space, slammed through the Earth's atmosphere and lit up. So you can really see how the Earth is active because of our sun. And I think that's the great thing about the aurora is you can really see it come into play with your own eyes if you're really lucky to. Now the sun's quite quiet. It goes through active periods and less active periods. We're in a very less active period now. In a couple years, we'll start getting more sun, what we call coronal mass ejections and sunspots. And so we'll start getting more stuff happening here on Earth. Now, that video shows something really cool. I think it's very important that we all have to understand, and that is day and night. So this is kind of a nice image of Australia from space. And you can immediately see already, here on the left, it's already in nighttime. So because of the position of the sun, as we spin around, as our planet spins around, our planet spins on one time every 24 hours, just about. And so that's why every day and every night comes around, we spin around. And when we're in daytime, the other side of the Earth is at nighttime. Now it's a fairly simple thing I think we all experience every day. But it's always realizing to see that it's actually because our Earth is spinning that we have day and night. So imagine right now the Earth stops spinning. Whatever side you're on, it would be stuck like that. You would be stuck in daytime or you'd be stuck in nighttime. It wouldn't come in 5 hours or 10 hours or 3 hours, depending on where you're looking and when you're looking. It would just stop. And therefore, you have no day, you have no night. So if you're daytime, you have to be awake. If you're nighttime, you have to go to sleep. And there are some planets around other stars like this. They're in a position where they only have one side that has daytime or one side that has nighttime. And this means life, if they're on those planets, would have to be really different. And even some of the planets in our own solar system have weird features like this. And one of the, I think the things that we can see is, this is again another video from space, that as the Earth rotates, you can actually see our lights. You know, we talk about light pollution in space, in astronomy, because those lights that light up our streets can be seen from space. You can see, especially where the big cities are. There in the US, you can see lots of the big cities. We're about to come here to Australia. And you can start to see our nighttime. So you can see, I can see Sydney and Canberra and Brisbane and Melbourne and a few other places. You can really see where our brightness is. And you can especially see in Asia, the big bright spots. So you can see our nighttime and our daytime quite clearly from space. So not only can we look out and stay on Earth, and as we rotate, we have daytime and nighttime, you can see daytime and nighttime from space on Earth. And that's an important thing to think about, is how our planet spins is directly related to how we live our lives. And it wasn't always like this. The day wasn't always 24 hours long. It has to do something very cool that we call the moon. And we'll talk about that in a second, because there's something else really special about our Earth. And that is, it's actually kind of tilted on its side. So when we spin, we're actually spinning at a slight angle. So you can see here, it says we're kind of tilting. We've almost fallen over by about 23 degrees. So imagine standing up and leaning a little bit to the side. Well, that's our Earth spinning around. Now, some planets like Mercury don't have really any tilt at all. Some, like Uranus, are almost on its side, like it's rolling around. Some are quite close. Mars and Saturn are pretty close to the Earth. But Uranus is very different. Venus is very different. Now, do you know what this tilt does? It creates something very important that just kind of happened to us recently, and that is the seasons. And because our Earth is tilted, we actually have seasons. So sometimes you think we have seasons because the Earth is closer or further away to the sun, and that's actually not quite right. It's because we're a bit tilted on its side. So let's take June here. So June here, it's in the middle of winter in Australia. And because the Earth is tilted in a way such that the northern hemisphere is tilted towards the sun, the northern hemisphere gets more light, and therefore it has longer days, and therefore it heats up, and we get summer in the northern hemisphere. Now, because in the southern hemisphere, we're tilted away, we get less light, shorter days, longer nights, and we get winter. But the reverse happens. So in December, the southern hemisphere is tilted towards the Earth, or the sun, and that means we get summer, and the northern hemisphere gets winter. But what happens in between? What happens in March that we just had, March 20th, and in September? We get what's called the equinoxes. And that is where the tilt is essentially side on, so the northern and southern hemisphere get equal amounts of light. They get equal amounts of heating. The daytime and night times are fairly similar. Now, have a think about this. If you're living here in Australia and the seasons we get, what are the seasons like in the northern part of Australia versus Tasmania? You might realize that day and night is always a little bit more the same across all of the year, and say places like Darwin, the temperature is very similar. Places along the equator are always getting similar days and nights across the year. But at the poles, so let's go to the North Pole. In the winter in the North Pole, you get no sun, sometimes for about a month, same in the southern hemisphere. So really where you're tilted gives you the effects of the season. So someone just asked, if the Earth wasn't tilted, what would happen? That's a good question. What would happen if the Earth wasn't tilted? Have a think about it. And the best way to think about it is, what would happen on the other planets? We wouldn't have seasons. The day and night would be the same all year round. That would change the heat. That would change the light. Now, this is a really cool time lapse that shows this. So this is taken from one of the NASA space telescopes. And what we'll see here is over the course of the year, we'll actually see how the amount of light changes on the Earth. So over the course of the year, you can see now the northern hemisphere is getting more light. So peak in the solstice, and now we're going closer to the equinox. You can really see this effect. Let's just play it again. So here we're going into the southern hemisphere summer. It's about December. Now we're getting the equinox. We just had that in March. Now we're getting into the winter here in Australia. And now we're coming back into spring. We can really see this effect. And if we didn't have this tilt, we wouldn't have these seasons. Now, you can't really feel this tilt, and that's because gravity's pulling us down. You don't feel it, but we see it. And we see it in the way our planet moves. And we also can compare this to the other planets. So have a think about this today, after this. When we do our demo, what would the seasons be like on the other planets? What are the seasons like on Mercury? What are the seasons like on Uranus? It's kind of like fallen over. What about Jupiter? What about Mars? Mars's seasons are probably similar to the Earth, and in fact, we know this. But what about Mercury? And Uranus is even strange. So it's kind of interesting how this tilt has really allowed us to have the seasons that are quite important. Now, I mentioned this a bit earlier, our moon. Our moon is quite important. You can see it tonight, and you can see it a lot of nights, depending on when you're up. Now, the moon has really special properties in the sense that of what it does to our Earth. And it's also quite a special thing itself. In fact, you can see one of these special things right now. So these darker areas are what we call Mare. And you can see these with your own eyes. If you can go outside, you can see some of the darker areas and lighter areas. And these darker areas are actually old volcanic lava flows. This is lava, essentially, that used to be on the moon and hardened. And you can tell, if you look here, there's less craters in these darker areas than these lighter areas. So think of places like Hawaii. Now, someone just asked, can you see the dark side of the moon? This is a great question, and I'm about to get into, because there is no dark side of the moon. There's what we call a near side and a far side. Now, firstly, to understand this, we have to talk about how our moon was formed. So we actually think billions of years ago when the Earth was just forming, something slammed into the Earth, and then a whole bunch of rock and lava spilt out. And this formed around the Earth and eventually came into a clump that we call the moon. The moon actually came from the Earth. The moon used to be a part of the Earth. Now, one of the reasons we think about this is one of the big successes of the Apollo missions. The Apollo missions did lots of studies of the geology of the moon and the Earth. And in fact, you can hear from someone who knows a lot about this in a couple weeks. And so we now know, or we think we know, that the moon used to be a part of the Earth. And because of this, the moon and Earth have formed in a very special kind of lock. Now, this was actually taken from one of the NASA satellites, and I think it kind of is cool shows here. You're seeing the far side of the moon, the dark side. So imagine the Earth and moon as a giant rope between. And so there's always a side that faces the Earth, and there's always a side that faces away from the Earth. But the side that faces us sometimes is light and sometimes is dark. So sometimes we see the moon, sometimes we don't. And this is actually related to the phases of the moon. So there is no dark side of the moon, there's just a far side of the moon. But this photo is showing the far side. But what you notice is the far side has light. And that's all to do with where the moon is in relation and in position to the Earth and the sun. And so the other cool thing I think that you see is that how small the moon is. The moon is only about the size of Australia. It's not very big. And someone just asked, actually, what is the moon made up of? Eloise tomorrow on the Mount Charlemont Facebook page will be talking exactly about this. Now, you can actually see, so this is a little bit of a video showing how the Earth is moving. So as the Earth rotates, the moon moves with it. So again, imagine a giant rope is stuck between the Earth and the moon. And we're going to do this in a second to show how it works. And as it moves around, we get to see it move, but it also relates to something very important, and that is the phases of the moon. So let's have a little simple diagram here. So we have the Earth, and we have our moon going around it. Now remember, we only have one side that faces us. Now, so a few days ago, we had the side that was facing us almost perfectly in a line with the sun. And when that happens, it's all lit up. It's what we call a full moon. And then as it moves around, we start to see less and less of the moon. but the same side still faces us. So we go from a full moon to a half moon. Now, what happens when there's no moon? It's what we call a new moon. So the side that's facing us isn't in sunlight. It's the far side, or what we call the dark side, that is completely lit up. So there is no dark side, there's just sides that we can see. Now, the cool thing about phases is this happens to all sorts of things. So this is exactly what the phases look like here from Australia. So we have the full moon and we have the new moon. And so depending on where you are in the hemisphere, the moon is lit up differently. So imagine you were in the northern hemisphere. Well, you actually kind of go this way in terms of brightness. And if in Australia, we go this way. And that's actually kind of, imagine just standing upside down and what the moon is moving alike. And again, we're going to do a demo that shows us because you can really see how the phases work. Now, someone just asked, how long does it take for the moon to rotate the Earth? So it takes 27.3 days for the moon to move around the Earth. But it actually takes 29.5 days to get from phase to phase, from full moon to full moon. So why is there a difference? Well, it just so happens that because as the moon moves around the Earth also moves through space. So the moon is always slightly catching up. So it takes a little bit longer to get in the same position to the sun as it just does to move around the Earth. So it's kind of a cool way of actually seeing our Earth also moving through space. Now, I really like this. This is the phase of Earth. So let's imagine here. Let's imagine we're a half moon. So we are here in Australia and we look up and we see a half moon. What happens when we look back at Earth? It's half as well. So any planet, depending on where it's positioned, can actually have a phase. Here's actually a phase from a satellite taken of both the Earth and the moon. And you can see they're exactly similar. The sun's here on the side, and the same amount of light is falling on the moon as well as the Earth. And we're going to talk about eclipses in a second because this is all kind of related. And you can actually see this with your own eyes right now. So in the early evening, in the western skies, you have this really bright dot, and that bright dot is called Venus. Now, Venus has phases just like the moon does from Earth. So if we play this little video, so what you'll see here is we started to see Venus in the early skies in the evening in January and February. And right about now, it's about half Venus. And then it's getting into 30 and 20 and 10% Venus. So if you go tonight, or any night, and you have a pair of binoculars, or a telescope is better, but a pair of binoculars is great, and you stare at that bright dot in the western skies, you won't see a very full circle. Right now, you'll see it kind of about quarter Venus. And if you looked a little bit earlier, it would have been half Venus. And then if you keep looking, more and more will disappear until we can't see it at all. So you can actually see the phases of an entirely different planet. And this is one of the big things that Galileo used to prove the Earth wasn't the center of the universe. So it's a really great question. And someone just asked, what is an eclipse? This. So this is what we call a solar eclipse. And that is when the moon is in between the Earth and the sun. So the moon just so happens that it's 400 times further away than the sun, but it's 400 times smaller. So the size appears to match up from the Earth with the sun and can completely block it out. But we can also have lunar eclipses. And that's when the moon actually goes into the Earth's shadow. So let's take a look at this. So we have the Earth, and the moon spins around, and it happens to be in between the Earth and the sun. And so it blocks out the sun and creates a little shadow here on Earth. Or as the moon goes around, the Earth actually casts a shadow into space. And as we cast a shadow into space, the moon gets darker, but then it turns red. And this is a really cool thing. A little bit of light goes through our Earth's atmosphere and lights up the surface of the moon, turning it red. So it's kind of like seeing the sunrise and sunset of the Earth falling on the moon. Now, if we go back to our phases real quick, in order for a lunar eclipse to happen, the sun must be hitting the Earth and casting a shadow into space. So a lunar eclipse can only happen when the moon is in a full phase. And in order to get a solar eclipse, the moon has to be in between the Earth and the sun, a new moon phase. And when the new moon is happening, you would get a solar eclipse here on Earth, but you get a different eclipse on Earth. So it's a really cool way that the Earth, Moon, Sun works to create things like the seasons, daytime, nighttime, eclipses, phases, all sorts of things that you can go see with your eyes. You can go see the phases of the moon tonight. You can see phases of Venus over the next few months. Now, I'm going to stop sharing, and let's do a little bit of a demo, okay? And then we'll take some questions. So I have a little Earth. I have my little astronaut, my Lego astronaut here to Earth. And I have my moon, so just a black ball. It's a Cars ball. So we'll say this is the side that we can see, the Cars side. And if you notice, I try to get these kind of similar to scale because the moon is about the same size as Australia. It's not that much different. Now, the moon moves around the Earth, as we talked about. And so you can do this at home. You just need some ball, and a smaller ball, and to get your sun, a torch. So I'll turn on my sun, let there be light. Now, as our moon moves around the Earth, what do you see? You see a shadow. So when our moon is in front of the sun, here, and the Earth, we get a solar eclipse. We're blocking out the light. Just put my torch up here so we can see a little bit better. So as I move around, there goes my eclipse. So we're going to eclipse Australia right now. Let me position Australia here. So here we go, and we're having a solar eclipse right now. Now, if I move the Earth into it, the back, so we have the moon in the background. So it's a bit hard to see here. And we have the Earth. We're actually creating a shadow. We're blocking out the light from the moon. And therefore, the moon is now having a lunar eclipse. Now, remember we said we can only see one side. We'll say this is our car side. Now here's our car side facing Australia. Now, as we move around, we can't see it lit up. So now the backside is facing us. So the backside, because it's not getting enough light, we don't really see it. But it's still facing us. Now, the backside of the moon now, so see, our car side, the side we can see is facing us. The backside is getting lit up. So the dark side is not the dark side now, it's the light side. So as we come around here, lit up, this side lit up. So the moon and the Earth are in essentially this giant rope, and we can't really figure out, or we can kind of figure out what happened, and we think it's all related to how the moon and Earth was formed. But we can actually see that as the moon moves around, we get our phases. And so go into a dark room, take a ball, take a smaller ball and a light, so a torch, and turn off all the lights. And then you can actually start doing the phases as it comes around. You can start seeing the different parts of the ball lit up. And so I'll do a separate recording of actually just doing this demo in a very dark room so you can see it. And so just using these three simple things, we can create the tilt. So let's tilt our Earth. So right here, now the northern hemisphere is tilted more than the southern hemisphere. So there's more light here. Now we're going to come into our summer. We have more light in the southern hemisphere, less in the northern hemisphere, summer. And what happens at the equinox? We're equal. And so you can really start to see how the phases, the eclipses work, and also seasons. And it's all because we have this moon, this Earth, and our sun. Now I'll just take this away. Now we've had a bunch of questions, and someone just asked, is the moon and sun opposite? Well, no, the moon always moves around the Earth, and it moves around every 27.3 days. We see it every 29.5 days. So when the sun and moon are opposite, we see one side, the side that we can see in full. When they're on the same side, it's not lit up because there's no light on this side, and we get a new moon. Now, someone just asked, why couldn't I see the moon last night? Well, that's because exactly this. It's taking time to rotate. So every 29.5 days, it takes time to loop up. So you actually can see it if you're just staying up a little bit late. So now the moon is rising about 10 p.m. And so it changes about every hour. So if you'll go out a little bit later, you'll see the moon rise. And what you'll notice is when you wake up in the morning, this moon is still in the sky. And that's because you can still see a little bit of it during the daytime because it's bright enough to reflect a little bit of light. And if you give it a few days, it won't really be visible at all. And then if you wait about another week, you'll start to see the moon just popping out in the early evening just for a little bit. Now, why doesn't the moon affect the tides? Well, the moon and Earth are, imagine there's a giant rope. Imagine this, and it's tugging on each other. As the moon tugs on the Earth shakes. What's the kind of that shaking? Tides. Now, the cool thing about it is we think the moon used to be closer to the Earth. So remember, something crashed into the Earth, a whole bunch of stuff fell out and created the moon. And we've known with the Apollo missions that the moon is slowly drifting away. And as the moon drifts away, the tides will get weaker. And this actually slowly changes our rotation. So the moon is actually causing the Earth's day to get a little bit longer. So we know around the dinosaur era, the day was about 23 and a half hours long, not quite 24 hours. So even about 70 million years ago, the day was a little bit shorter. Scientists have actually been able to measure this. And that means the moon was a bit closer, and so the tides were a bit bigger. Now, someone just asked, do some planets not have any moons at all? Yes, Mercury has no moons, Venus has no moons, Mars has 2. The current record holder, what's the current record holder? It's Saturn at 82 moons. Jupiter has 79. Now I'm going to talk more about next week about the solar system. Sorry, there is no actual rope. What we call the rope is gravity. So gravity is like this imaginable, visible rope tugging between the two. So gravity is the same thing that keeps us, the Earth, and there's a gravity, this force that's keeping the moon and Earth together. Just as the same as the gravity of the sun is keeping the Earth moving around it. Now, a new moon is in that point where the side that we can see, our car side, is essentially in between the sun over here and the Earth. So there's no light on this side, so we just can't see it. So we have to wait a little bit longer, so we get a little bit light. See, you can now start seeing it. Now we can almost see it perfectly. So you just have to wait to see it. And that's actually what happens for the phases. What would happen if the moon or sun did not exist? So this is a good question. If the sun didn't exist, we wouldn't exist. If the moon didn't exist, what would happen? Our tilt would be different. So we think that big collision that created the moon also kind of knocked us a little bit, and that helped create us our tilt. And if we didn't have that, we wouldn't have seasons. Now, if we didn't have the moon, no tides. Our day doesn't change. So a lot of different things change if the sun and moon and Earth don't work the way they do. So we're very special. They kind of all are working their way they can. Does the sun have a moon? No, only planets can have moons. Suns, stars have planets and a whole bunch of other things. Can a moon have a moon? So we have detected, astronomers think they've detected a moon that's orbited a moon. So you have a star, and the moon, planet goes around it, and then a moon goes around that planet, and a moon goes around that moon. We call them moons. We kind of need a better name for that, but currently there's moons. So, I really think that, because of the Earth and moon, someone asked, do we need the moon to survive? We really do. We need the moon to survive in the way that we think. How does a blood moon happen? A blood moon is a total lunar eclipse. So here we have our moon. It's behind the Earth. It's in the Earth's shadow. And so the Earth is mostly blocking out all of the light on the moon, except a little bit of light skirts around the Earth's atmosphere. So kind of imagine like a sunrise, right? The sunrise is always a bit reddy, orangey color. A little bit of that light comes to the Earth's atmosphere, lands on the moon, and turns it red. So you're really seeing the sunrise and sunset of the moon, or of the Earth, at the same time lighting up the moon. And that's what we call a blood moon. So blood moon only happens at a lunar eclipse. How fast does the Earth rotate around the sun and the moon? So how fast does the Earth rotate around the sun? Well, 365.26225 days. We call that a year. Now, a year is not exactly 365 days. So every so often, we have to add what's called a leap day. And we just had a leap day in February. And that's because it actually is about 365 and about 1/4, or about 6 hours of a day. So every 4 years, we add an extra day in the calendar to make our calendar and our year essentially balance out. If we are moving, does that mean the clouds stay in one place? No, the clouds also move on the Earth, and that's because there's things like winds and stuff blowing around it. Our eclipse is always at a daytime. Depends on the eclipse. A solar eclipse is always happening during the daytime in order for you to see it, because the sun and the moon and the Earth must line up in the same spot. See my shadows happening over Australia. A lunar eclipse will always happen at nighttime, because the Earth needs to be in between the sun and the moon in order to cast the shadow. So a solar eclipse always happens when the moon is a new moon during the daytime, and a lunar eclipse always happens when the moon is a full moon at nighttime. How does a supermoon happen? This is a great question. We just had a supermoon, what we call a perigee-Syzygy moon, which is a very technical term for saying that perigee, the orbit of the moon, is not perfect. Sometimes it's a bit closer, and sometimes it's a bit further away. So the orbit of the moon varies by about 50,000 kilometers. So on average, the moon is 384,400 kilometers away, or it would take about 5 months worth of driving if you could drive to get there. But it changes by about 50,000 kilometers. So when the moon is a bit closer, we call it a perigee moon. Now, Syzygy is a very technical, weird word for saying that the Earth, moon, and sun are all in a line, otherwise known as either a full moon or a new moon. So a supermoon happens when generally you get the moon a bit closer and it's at full phase. So if it's a bit closer, it looks a little bit bigger and it's a little bit brighter, hence supermoon. You can also have a mini moon where the moon is a bit further away, so it appears a bit smaller and a bit darker. Now, there actually is a difference you can notice. You wouldn't notice it with your own eyes, but if you take a photo of the full moon at a perigee phase and the moon at apogee phase, or that micromoon, you can see a difference. Now, someone asked about black holes. There's a lot of black holes, and in a couple weeks, we'll be talking only about black holes. We'll get into every detail you want to know about black holes, so stay tuned for that. How do we get a blue moon? So a blue moon, it is not actually blue, sorry. Our calendar, our month, usually is about 30 to 31 days. Well, it takes 29 and a half days to go from full moon to full moon. So a blue moon happens when you get 2 full moons in the same month. So let's say we get a full moon on July 1st. Well, 29 and a half days later, about July 30th, you can get another full moon. So you have 2 full moons in the same month, what we call blue moon. It doesn't look blue, unfortunately. It'd be kind of cool. Do lunar eclipses happen more often than solar eclipses? This is a very, very good question. So firstly, let's ask, why do we get solar eclipses every time the moon is in a new moon phase, or lunar eclipses when it's in a full phase? If the moon is doing this, how come we don't get eclipses every 14 or 29 days? And that's because the moon wobbles a bit, changes by about 5 degrees as it's moving around. So it's not always perfectly in the spot of the sun and the Earth. Now, what is easier to happen? Well, we actually do get lunar eclipses more than solar eclipses because the Earth is bigger and we cast quite a big shadow. For a solar eclipse, a total solar eclipse to happen, you have to be in that very specific spot so that we're casting a shadow right into the spot that you're looking. So solar eclipses happen, total solar eclipses happen less than total lunar eclipses. It's a very good question. And because the moon does this wobbling, there's a really cool thing that happens. It doesn't wobble that fast. So if you ever have a solar eclipse somewhere on the Earth, 14 days later or 15 days later, you're always essentially going to have a lunar eclipse because that kind of wobbling is in the same perfect circle in that time. Now, we'll just do about 1 or 2 more questions and then we'll finish. How long does the Earth's phase cycle from the last moon? So the moon phases take about 29 and a half days. Now, what I'm going to do is I'm going to give you all some homework. I want you to find a ball, a smaller ball, and some sort of light. I want you to go and think about how do the phases work with other moons on other planets. Saturn has 82, Jupiter has 79. What about Mars? Mars has 2, Phobos and Deimos are tiny. How do the phases of those moons work? What do they look like? What do the eclipses look like? Now, Mercury and Venus, they don't have moon, so we can't do that. So let's look at Mars. Think about what do the eclipses of Mars look like. I want you to go home and do that. Figure out how the eclipses and the phases work of those moons. Now, the other thing to think about is how do the seasons work? Again, take your bowl, and I showed you the image, and I'll put up, actually, you can go back to the recording and see the tilt so you can look at them. So Mercury doesn't really have a tilt. What do the seasons look like? Uranus is like that. What are the seasons like on Uranus? Mars, it's pretty similar. Now, we have 2 more questions. Or I'll go 3. Does that mean the moon moves in an elliptical orbit? Yes, the moon does move in an elliptical orbit. There is essentially no such thing as a perfect circle orbit. They're always slightly elliptical. Even the Earth's orbit is slightly elliptical. So there are points, what we call perihelion and aphelion, so where the Earth is actually slightly closer to the sun and slightly further away. There's very minimal difference, and we don't really notice it. And again, that's not what causes the seasons. It's all about the tilt. What will happen when the moon gets too far away from the Earth? Well, if it's long enough, we'll slow down. Our day will keep going slower and slower and slower until it could stop, and we stop getting tides. And in fact, the Earth's rotation is slightly out of sync. And every so often, we actually have to add a leap second. So we may have a leap second here in December. We can talk about that another time, because leap seconds and leap years are really cool. And someone just asked, and we'll end on this. Well, there's 2. I see 2 good ones. Sorry about all your questions. There's a lot. That's great. We'll try and get to them. And remember to stay tuned tomorrow. Eloise on the Mount Sharma Facebook page will talk all about the solar system and how they're made. And you can ask more of these questions. And next week, we'll put the schedule online shortly. We'll talk all about the rest of the planets in the solar system. Are all moons smaller than the planet it rotates? Essentially, yes. But it's not always perfect. And we'll get into that because that relates to Pluto. This actually starts to get into the whole Pluto debate. And we'll talk about that more next week. And do I advocate for a lunar calendar as opposed to a Gregorian calendar? No, because again, the lunar cycle isn't perfect either. I think the Gregorian is a great way of trying to estimate it. We kind of need something in between. And that's the kind of cool thing. We're trying to make a math to fit perfectly in with what happens with the Earth, Sun, and Moon. And it doesn't actually fit exactly to the numbers we can. If we want to be really specific days and months, we probably could have a better calendar system. But I think as of now, it's good. It works for me. I hope everyone had fun. I hope there wasn't too many technical difficulties. Thanks for tuning in for this first one. Again, the recording will stay on here. You can rewatch it as many times as you want. We'll post the schedule for more talks coming up. I hope everyone enjoyed it and have a good week. And I'd love to hear about how your own Earth, Moon, Sun experiments go at home.